Go to the computer. Hello, all. Good afternoon, good evening, everybody. Welcome to the latest Flight Crowds webinar. In fact, it's not just a Flight Crowds webinar, it's a Flight Crowds Engineer Insight Group webinar. Welcome to those of you who are joining us for your first session, or those who are returning, and hopefully you've been enjoying our webinar series so far. Let us know in the chat if you have attended many of our sessions, or this is the first one. Let's see how many of the returners we get and how many newbies. Welcome to all. In the meantime, I want to mention that myself, I will not be the main guest of the show. I am very privileged to be joined here today by my flight card colleague, Lydia, who's the co-chair of the Engineers Insight Group. But more than anything, our speaker, our wonderful speaker, Richard Brown, who will be taking you through the presentation later today. I can see a couple of people already messaging the chat, which is brilliant. Let's see who have we got in the audience? So, we can see somebody has been attending all of our webinars. Brilliant. William, you get the biggest brownie points. And then we've got somebody who's currently on our Open Skies Pathways program. Fantastic to have you back with us, Jack. And yeah, I can see you've already attended our Pilot Insight webinar yesterday, so now you're back for the engineers. Great. Hopefully no favorites. All of our webinars are brilliant. All career pathways are brilliant. And hopefully this is one of the purposes of today's session, is to put a spotlight onto a brilliant engineer's career, put a spotlight onto a career pathway that maybe not all of you have considered in the past, but also tell you something exciting about the sector that we are passionate about, and the sector that is developing so fast. In terms of the format for today's session, some of you who have been to our previous webinars, you may be familiar. We're going to have Richard going through the presentation, and then Lydia and myself will do a moderated discussion after the slides, and then we'll of course have the opportunity for you guys to ask some questions as well. Please feel free to drop your questions in the chat anytime during the webinar, and then we'll somehow find ways to intertwine them into our discussion. Anyways, hopefully that's all okay. Also, just before I forget, do let us know, guys, where are you in your career? That's something that we always ask all of our participants. We want to make sure that we tailor the webinar to your interest, to your background, and your experience. Are you currently in school, in college, in university? Are you looking for opportunities? Let us know in the chat. That would be brilliant. And then hopefully it will also help Richard, so that I think, Richard, you said last time, so we know whether to throw in there some maybe Stokes equations, or maybe leave them for another time. So I can see I've got somebody from year 11, so currently in school. Brilliant. Let's see who else I've got. Year 11, year 12. Year 12, aspiring to become an airline pilot. Okay, but Jack, we'll see. We'll see. Maybe you'll change your mind after today's session and actually consider a career in engineering instead. We've got somebody who's doing a gap year. Brilliant. Thank you. Oh, I wonder if we have anybody from university at the moment, or recent graduates. Let us know if you are. But it seems like, Richard, you've got quite a young, keen audience here in the group. Fantastic! I can see recent PhD graduate and master's graduate. So we're pretty much covering quite a big range. Wonderful. Well, welcome to everybody, and thank you so much for interacting. Enough about me, because as I mentioned, I'm not going to be the center of attention. Can I now hand you over to my colleague Lydia for a quick introduction to yourself, and of course welcoming our guest Richard. So Lydia, over to
Thank you,
yourself.
Maria. Hi everyone, and welcome to the second webinar of the Engineers Insight Group webinar series. I'm Lydia, I'm the co-lead of the Engineers Insight Group, and today we have the honor of having Dr. Richard Brown as our invited speaker. I'm going to briefly introduce Richard. So Dr. Richard Brown is an experienced aerospace engineer with over 30 years of work in aircraft and rotorcraft aerodynamics, air vehicle design, and aerospace education. He has supported organizations worldwide in developing aerodynamic tools and delivering innovative solutions to complex design challenges. And in 2023, he was awarded the Royal Aeronautical Society Bronze Medal for his contributions to the rotorcraft aerodynamics. So without further ado, Richard Brown. The floor is yours.
Thank you very much, Lydia. Yeah, and welcome everybody. I'm going to take you on a bit of a journey. I'm going to start last week, I guess, with the launch and recovery of Artemis 2. But most of the start is actually going to take me back to a much earlier period, the period when I was a youngster and trying to decide what sort of career to follow as my life developed in front of me. So I'm not going to take you back quite as far as 1953, but I hope some of you recognize this picture here from one of the most influential books on my life, and that's certainly the case, which is this one over here called Explorers on the Moon, written in 1953 by Hergé, dealing with the adventures of a young reporter called Tintin and his colleagues as they went on various adventures through the world, essentially. But let's not go back to 1953. Let me take a little bit of a step forward into the future and go back to the 1960s, when I was born, 1966 to be precise. Now, it's difficult to imagine the world of 1966 and of the late 60s. At that time, what was happening was that the United States and the Soviet Union were engaged in this race to put a man on the moon. That was the sort of the broad headline, if you like. But just the kind of space mania that existed. If you went to the garage to get a tank full of fuel, you'd get stickers for the Apollo missions. If you went to the supermarket, you would get space branded cornflakes. If you went to the local haberdashery, they'd have a big model of Neil Armstrong standing in there to welcome you into the door. So it is very difficult not to be influenced by this kind of environment and not to have that absorbed into your DNA in some fashion if you grew up in the 1960s. And these various images that I've shown here are particular examples of the sort of iconic imagery that kind of sticks in one's mind from the 1960s. Now, I was a small child, if you like, in the 1960s, very small child, and most of my growing up was done in the 1970s and 1980s. Now, to a small child in the 1970s, this was an incredible adventure. There were these people setting out across the universe to try to establish a foothold on a different planet or a different celestial body. The moon was the first in the sequence of places that were going to be visited in succession as we spread out across the galaxy. Now, this guy over here, of course, was a 1970s style superhero. If you had model rockets, you were absolutely the thing. And of course, you could also, for the princely sum of $6.98, you could buy yourself an entire Polaris nuclear submarine, big enough for your friends to be able to sit in and launch nuclear missiles. Not too sure who at, perhaps your neighbors. But as I said, the most influential work in my youth was this particular book over here, Explorers on the Moon, Hergé, The Adventures of Tintin. And that was bought for me as a 4-year-old after a lot of pleading and begging of my mother to put forward the funds that were required to get that book. Now, as I grew up, as I became a teenager, my interests kind of changed a little bit. I realized that perhaps the adventure was one thing, but the science, that was the really interesting thing. How is this actually done? So if you go into Explorers on the Moon, there's this fantastic diagram here of Tintin's rocket, the moon rocket, and how it was actually laid out. And those sorts of images really captured my imagination. And as my intellect evolved through schooling and education, I started to realize it was the aerodynamics, it was the physics, it was the mathematics that were really the things that grasped me. So I'm sure many of you recognize this vehicle over here. If you do, stick it in the chat, and and you can see that it's got some really interesting flow phenomena going on here. There are these things called shock waves, which really captured my imagination, which are to do with what happens if this vehicle accelerates up to near the speed of sound and then finally penetrates through the speed of sound. You end up with all these really interesting aerodynamic patterns. Exactly, Maria, you're 100% right there. It's the space shuttle. Okay, so by the time I finished my schooling, I knew precisely what I wanted to do. I wanted to be an aerospace engineer. And what I did is I enrolled I should have said at the beginning that I grew up in South Africa. So I enrolled in the University of the Witwatersrand in Johannesburg for a degree in aeronautical engineering. Failure wasn't an option, of course. And this is the picture of my classmates on the very last day of studies, the 5 of us that finally made it through this degree, plus our lecturers sitting in the bottom row over here. And I'm not too sure, is anybody here from Bristol University? If you are, stick up your hand quickly. I'm sure you'll recognize, if you are from Bristol University, you'll recognize his character over here. It's Professor Mark Lowenberg, who was one of my very influential lecturers at the University of the Witwatersrand. And certainly we felt like these guys, the Mercury 7, we felt like astronauts ready to launch on our career into wherever it was going to take. And at that time in South Africa, a lot of really interesting stuff was going on. It was a time when a lot of money was being invested into aeronautical development, especially in the area that I was really interested in, which was high-speed flight. It was the idea of becoming a fighter aircraft designer. And this is not a South African aircraft, but very, very similar work was going on at a particular company lying just outside Johannesburg, where after I finished my degree, I managed to get a job at this Aviation, the dream job, working on an aircraft, something like this, and doing the aerodynamic calculations as this thing went supersonic. I found something really interesting. They weren't really interested in putting me in a job where I was doing the supersonic calculations of an aircraft like that. Instead, what I ended up finding myself was in a division where they were looking at these grubby things over here, helicopter rotor blades. These things were called fixed wing aircraft. They were so derogatory at the time that they actually went ahead and called these things loose wing aircraft. In other words, things with flapping rotor blades. But my first project was kind of relevant to my interests. It was to calculate the aerodynamics of airfoils, the kind of cross-sectional devices that are used in these rotor blades to give them their specific aerodynamic performance. Now, at the tips of helicopter rotor blades, you're really worried about the behavior as you go up near the speed of sound. So I was calculating the aerodynamic characteristics of these airfoils near the speed of sound. Where you ended up with shock waves, it was great. You could actually see these shock waves in the calculations that we were doing, these very primitive calculations that we were doing. Here's the date of this particular calculation, 1988-01-12, so at the end of 1988. And the problem was, of course, trying to get these calculations right. And it was over and over again, an iterative process. Run the calculation. Is it right? No, change a parameter. Go back, run the calculation again. And the work was interesting and it seemed fairly relevant, but it seemed really, really detached. You know, why was I spending hours and hours doing these airfoil calculations when what I really wanted to do was the design of full-on aircraft? So was it all just an exercise? Perhaps an endurance? Perhaps were they testing me? Perhaps were they seeing if I was fit for something else, or just what was going on? And this kind of frustration boiled over at one stage. And I tend to be quite abrupt at times. So I went to my boss and I said, what on earth am I doing here? Am I really doing something useful? And his eyes kind of went, whoa, what on earth? What's this guy? Is he challenging me or something? And he took me downstairs. And downstairs was an office that looked something like this, with about 100 people sweating over these drawing boards, all drawing up plans. And he said to me, what do you think these 100 people are doing here? Do you think we would not be doing something useful with these 100 people? Do you think they're all just wasting their time? And I had this feeling of absolute deja vu, because within this Tintin universe, there's a prequel to Explorers on the Moon, which is called Destination Moon, written by Auger in 1953, where Professor Cuthbert Calculus, who's like the protagonist of the story, is challenged by Captain Haddock to basically to say, what are you doing here? Are we just acting the goat? Are we wasting our time? And Calculus gets on his high horse and he takes them all on this tour through the factory. He says, and I suppose these people are acting the goat. And he gets really upset. And I thought, my goodness, I'm living the Tintin universe. And how the story ends in the Tintin book is that they get taken out, and this beautiful picture is what the first thing you see. It's this exposure, this revelation of this amazing rocket that's been built to take these individuals to the moon. And I had my amazing rocket revelation as well, because my boss took me into the factory. He took me through doors of increasing security. It was more and more difficult to get in until we eventually got to a room where they were building this amazing machine. Was under construction in the middle of this almost sterile hospital-like environment where they were all busy putting bits together to make something. And that was the Roy Falk CSH. CSH stands for Combat Support Helicopter. And this is 1987. I first saw the helicopter a little bit later than that, when it was in a slightly more complete fashion. But at that moment, I realized I've been wrong. What I need to do is helicopters. Helicopters are the thing. Forget the fixed wings. Loose wings are where it's at. 1989, the helicopter had advanced. It looked something like this. And by the time we got to 11th of February 1990, it had a nice coat of paint, it had all its rotor blades, and it was marched out of the factory in ceremonial fashion to the takeoff pad. 11th of February 1990, they fired up the engines, pilots were inside. after a little bit of a period of checking the machine over, eventually they pulled in a bit of collective, and lo and behold, the machine actually took off. All our hard work had come to fruition. And that was a huge moment in my career. Unfortunately, a few days later, the test pilots came back with some problems. Effectively, this aircraft couldn't fly sideways. And we wondered, oh my goodness, what have we done? Have we made some tremendous mess? And essentially we had. We'd mispredicted the aerodynamics of the tail of this device. And essentially through a long process, what happened? A whole load of variations of the design, cutting bits off, sticking bits on, changing the design. This is the prototype version here with this enormous tail fin. By the time they went into production, what they'd done is they'd cut away just about everything that we had designed onto the tail there. And they'd left electronics effectively to do the hard work. So aerodynamics was kind of sidelined. And what they did is they said, okay, we'll design an electronic box which will compensate for the lack of tail that we now have on this device. So it was a bit of a back to earth with a bump, as I've titled this slide. Essentially, what we realized is that there was something wrong with the aerodynamic tools that we were using to try to analyze these kinds of vehicles. Helicopter aerodynamics is incredibly complex. It's perhaps the most complex aerodynamic field to get involved in because the rotor blades generate these very complex swirling flows. And all those swirling flows from all the different components tend to interact in a very difficult way to predict. And if you went back to the 1990s, which is where we were now, then the kind of tools that we had were really, really simplistic. Computers weren't all that big. We had to be very careful how much we tried to squeeze onto the computers. And the kind of realism that we got out of those simulations wasn't particularly good. So I decided to devote my career at that stage to improving these tools, trying to figure out a better way of analyzing aerodynamics of helicopters. Now, in late 1990, what I managed to do was to get to Cranfield University here in the UK to do my master's degree in a new and developing subject, which was called computational fluid dynamics. And here's a picture of me in 1990, along with my supervisor, Tito Toro, and one of my good friends from Singapore, Misen Yip. Now, I'm not a tall guy, so it gives you an impression of the kind of stature of the guys that I was associating with in those days. But behind here, you can see some of the mathematics that we were developing. And what that mathematics suggested was that there was a novel and new way of actually going about formulating the governing equations of the fluid dynamics surrounding the helicopters that would enable us to make real progress in understanding how helicopter aerodynamics really works. Now, I kind of half promised that I wouldn't show any Navier-Stokes equations, and I lied. Here they are. This is the Navier-Stokes equations expressed in the usual form which CFD folk would use to solve the equations of motion. It's kind of like solving for the meat of the flow. You get an idea of the meat, of the velocities and the pressures. But what we realized is that you actually need to solve for the skeleton that underlies that meat. So what you do is you change the variables that you use in the Navier-Stokes equations, and you go about solving it in a different way. And this different way is what gives you the huge insights. It enables you to get down into the detail of just what's going on in these helicopter-related flows. So this is an early example of one of the calculations that I managed to do. It's a very simple vehicle. It's a gyroplane. It's got a two-bladed main rotor, and it's got a propeller at the back. And you can see that, yeah, we were resolving those wakes fairly well, fairly crudely, if you like. It's a very crude presentation, if you like. But we were actually starting to see some of the features that we were expecting to see. And indeed, when we did the numerical verifications against experimental data, we saw that we were actually making some good progress. So we were heading in the right direction. So this is about 1997-ish odd. Sorry, no, we're talking about, yeah, round about then, 1997. 10 years later, we were quite a long way down the track. If I try and run the simulation there, you can see the kind of thing that we were doing. Very complex aircraft, multiple rotors, all with these interacting wakes and giving us these very complex aerodynamic phenomena. And we were able to diagnose those and figure out what was going on. So this is the rotorcraft team in 2007. There are a lot of quite famous faces actually in there now, especially if you're in the Formula One world. Half the leaders of the aerodynamic teams of the Formula One teams around the UK happen to be in that particular picture. And since then, we've gone on to analyze the flows of many different types of rotorcraft. Now, things kind of never go according to plan. I think that's going to be one of the themes of this lecture. You tend to find that you're heading along a particular track, and all of a sudden you find that something really, really different comes along and just smacks you on the side of the head and says, okay, this is the direction you should be following. And that's one of the keys in establishing a career. It's knowing which of those directions to follow and which ones to kind of sideline and say, yeah, that'd be really interesting, but we'll leave that for someone else or another day. So the first intrusion of the real world was in 2000. These two vehicles were flying in formation across the desert near Marana, a small town in Arizona. And something really awful happened. One of the aircraft in that formation, in coming into land, tipped over completely on its back and crashed into the desert, killing 19 Marines, suspending the program and leading to a huge investigation as to what had actually happened. And nobody really knew, for a start, what had actually happened there. It became apparent quite quickly, though, that the aerodynamics of these vehicles was to blame. There was a phenomenon going on in the aerodynamics of these vehicles called the vortex ring state, which had been known about for many decades within the context of helicopter aerodynamics, but it wasn't realized just how susceptible vehicles like the V-22 with these side-by-side rotors actually was to this particular phenomenon. Now, you've probably not heard of vortex ring state before. It's essentially a change in the character of the flow around the rotors. So if we look at a conventional helicopter flying through the air in that direction, shown by the arrow there, then the wake that those vehicles produce is generally this long tubular kind of structure. The tube doesn't last forever. It breaks down. These individual vortices break down into these very unstable structures. And that breakdown is actually crucial. Well, understanding how that breakdown takes place is actually crucial to understanding the details of the vortex ring state. Because what happens under certain flight conditions when you're descending quite rapidly is that those products of that wake instability suddenly catch up with the rotor, causing it to change from having this cylindrical type form into having this rotational, toroidal, donut-like form in which the rotor ends up losing a lot of its thrust. And that's crucial, this change in wake structure, which causes the rotors to lose thrust under certain flight conditions. Now, there's a lot of junk, or at that stage in particular, there was a lot of junk written in the textbooks and in the academic papers about what actually caused vortex ring state. And I was very, very fortunate to have some brilliant PhD students. Gary Arlen is shown in this picture down here, and he was the guy who did a lot of the computations and a lot of the thinking, and also the help and partnership of a number of extraordinary gentlemen. This guy over here in particular, he's passed away, unfortunately, John Perry, who had a very strong pedigree as the design or the guy who's in charge of the Lynx that currently holds the world speed record and has for the last 40 years. And there is my father, who was also an academic professor at that particular stage. And what we managed to do, John Perry in particular, and Gary, managed to reformulate the way that we understand vortex ring state to be able to come up with a particularly simple way of predicting where on the flight envelope vortex ring state actually turns out to be a problem. So to get a little bit technical, there's the forward speed of the aircraft plotted along the horizontal axis and the vertical speed on the vertical axis. And there's this part of the flight envelope, this combination of forward speeds and vertical speeds over which the vehicle is going to experience this collapse of its wake into the vortex ring state. So that was a predictive method which could actually be used. And in fact, it's still used to this day. It's now widely used within accident investigation to actually have a look at vehicles which have entered into vortex ring state to determine just where and when that actually happened, and to try to make some sort of assessments as to how the aircraft ended up coming to harm in these post-crash forensic analyses. So here's an example from New Zealand where we did an analysis which showed that this particular aircraft definitely entered into the vortex ring state, and that explained why it ended up in that rather dismal looking state in the picture at the bottom of the diagram over there. Now, okay, how does it apply to the V-22? Well, it turns out that if you map that region onto the flight envelope, you can find this particular rather pernicious trajectory that you can follow, where perhaps one of the rotors on one side goes into vortex ring state while the other is left in clean air. And what that means is that this rotor over here is going to lose thrust. Pilot's tendency is actually to prop up that rotor by increasing the amount of thrust that he asks it to produce. And it turns out that's a completely the wrong thing to do, because what it does is it makes the situation worse, and it starts turning the aircraft upside down. And essentially, this asymmetric vortex ring condition was what was responsible for this accident at Marana. Particular characteristic of multi-rotor aircraft where the rotors are well spread out along the length of the wing. And that'll keep that in mind for the moment, because that'll come back to haunt us in a second. The real world then intruded again and kind of sent me off on a different path, the invasion of Iraq in March 2003. Now, Iraq is a dusty, deserty place for a fair proportion of its geography. And what that really means is that helicopters operating in those conditions tend to kick up a lot of very fine dust. And that's really not a good thing, because what happens is this cloud of dust comes up in front of the aircraft. The pilot trying to see out where he's trying to land on the ground suddenly loses all depth perception, loses the ability to judge how high he is above the ground. And a number of aircraft are being lost as a result of this so-called brownout phenomenon, this huge cloud of dust that came up and enveloped the aircraft. Now, in 2003, it was thought that this was just turbulence. Turbulence in the wake would kick up a load of dust, and that was it. But if you had a look at these pictures really, really carefully, there was a lot of structure in those clouds. And you ended up with these big streets, these pillars, this internal structure, which needed explaining. And it turned out that these very same instabilities that cause vortex ring state are responsible for causing the structure within the brownout cloud. And so we were able to come up with a new model which actually predicted very well just what was going on within these brownout clouds. And hence, we could kind of figure out, we could give advice to the manufacturers as to how their aircraft should be operated and eventually how they should be designed to be able to operate in these conditions slightly more effectively. Now, let's skip forward. Let's skip forward to 2026. We're living in a brave new world. These are the rotorcraft of the past, of the 1990s. These are the rotorcraft of the future, if you believe some of the hype. Multi-rotor, electric propelled, eVTOL type aircraft. The thing to bear in mind is these rotorcraft are far more complex than their forebears. You can see that the Royfalt there has got its one main rotor. The Joby S4, which is shown in that diagram over there, has got 6. How do we actually go about analyzing the aerodynamics of these highly, highly complex aircraft so that they will be safe in practice? So we need new tools that can address the challenge of making these new vehicles safe and reliable. And that's what we've been working on over the last years. Now, in the era of advanced air mobility, there are a number of questions that kind of come up, especially given if you've got experience from the past history of helicopter aerodynamics. So as we develop these new aircraft in all their multitude of forms, might we see some of these old problems like vortex ring state and brownout starting to reemerge, perhaps just in a different guise? Would these problems even be recognized and addressed, given an entirely new level or a new intake of aeronautical engineers who probably hadn't cut their teeth on the old helicopter programs? Commercial interests. These aircraft are supposed to be commercial. They're supposed to be coming into service to ferry you from your local downtown to an airport. How would those commercial interests interact with engineering sensibilities? So old guys like me saying vortex ring state might be a problem. How would that influence the commercial prospects of a particular aircraft? A couple of other issues which we can talk about perhaps in the question time as well, which is perhaps the idea of the visionary. The guy says, I have a dream. I can see 1,000,000 of these aircraft, or at least 1,000 of them, flying between Heathrow and central London every day. How does that gel with what we really know based on the science? And of course, short-term thinking, this idea of do we actually have the time and the effort available so that we can put in the groundwork so that we can develop a sustainable industry? And these are all problems that have really exercised me over the last few years. Now, our tools have advanced quite considerably in the last few years. So this is an old model. I've showed you that already from around about 2003. We can now do things like this. This you might not recognize. It's one of the latest and greatest eVTOL buses. So it's not going to carry 6 people to the airport at one time. It's going to carry 30 people at once. And you can see just the complexity of the aerodynamics of these particular vehicles there. And that's the kind of thing that we tend to have to model these days to make any sensible input into the design problem. So vortex ring state. Well, have a look. This is a sort of typical eVTOL plan form. And you can see this one over here has got eight rotors, all nice and widely spaced. So one of the real questions is, are these eVTOL aircraft subject to the same types of phenomena that the V-22 was? In other words, are they susceptible to vortex ring state because of this wide spacing of the rotors? And this becomes a particular issue when you start to marry that with ideas of how these vehicles are going to operate within the urban environment. So this is an EASA proposal for sticking a vertiport on the piazza outside the Cologne main railway station. Now you can see that if you want to fly into this particular landing site, because there's so many high buildings surrounding the landing site, you're going to have to go into a very rapid descending flight mode at the last minute to get down onto the ground. So does that have an influence on the vortex ring state for these particular aircraft? And it turns out that, yeah, you need to be a little bit careful as far as how you design your trajectories and your aircraft. There's another problem which has been exercising us of late, though, and that's pretty well shown by this particular picture here. Here's an eVTOL aircraft trying to come into a landing site. Here's another eVTOL nearby, and here are a couple of folks standing around absorbed or distracted, if you like, by the fact that this vehicle is about to do something. So what influence does this particular vehicle over here have on what these people are actually doing? So if we want to put that into scientific terms, essentially what we're doing is we're looking at a phenomenon known as outwash. So what happens is that in the process of generating thrust, a rotor accelerates air down through the rotor discs. And that downwards flow is there because the rotor generates thrust, and it's called the downwash. Now, that downwash hits the ground if the aircraft's flying fairly low above the ground and spreads out across the ground. And that flow is called outwash. Now, this kind of diagram over here is fairly anodyne. It doesn't really tell us terribly much. There's not much feature to that diagram. But what happens if you stick your grandmother into that flow, or a dog, or a suitcase? The kind of practical situation that you might imagine if you were, let's say, waiting for this aircraft taxi light to come and pick you up and take you off to the airport. And that's something that's exercised us at late. So we started off working with the Civil Aviation Authority, looking at large single rotor helicopters and trying to figure out just what effect that would have on people standing by. So this is the kind of thing that we would do. We would run a simulation, something like this. Here's an aircraft, it's a Sikorsky S-92, hovering at fairly low altitude above the ground. And what we would do is we'd stick a little computational person inside there with this little rake where he could measure the velocities. And we would run the simulation to see just what kind of velocities that we would measure. And that scale over there gives you an idea of the velocities actually experienced by that person standing there. So if I run the simulation, you can see the wake busy developing. You can see all these velocity pulses spreading out above the ground. And you can see that the flow that this guy experiences standing over there is highly variable. It's pulsatile. It changes from being 0 knots to 50 knots to 0 knots again to minus 10 knots to 30 in a very sporadic and unpredictable fashion. Now imagine your grandma standing inside there, being buffeted by this kind of wind. What kind of effects would that have on her? And that's something that's a really important question that needs to be answered in a lot more detail. And we don't fully understand the answers to that particular question right now. Now, that's for a conventional helicopter. What we've also done is the calculation for eVTOLs. And what you can see in this particular simulation here is if you thought the flow was complex for a conventional helicopter, then for eVTOLs, the problem is multiplied. The flows generated by these multiple rotors as they interact are extremely complex. So now imagine your grandmother standing in that. Which direction does she face? How does she brace herself? What does she expect where does she expect the next pulse to come from? And how will she then be able to sustain herself or to be a safe passenger within the environment of one of these particular vehicles? Well, these are just simulations. These are, and I put a big just there because they're actually very realistic simulations. But how do they compare to reality? And in fact, folk are actually trying to do that. So over in the United States, for example, here's the Joby aircraft having its outwash characteristics measured. The problem is that there's a tendency within this community to rely very heavily on past experience. Now, where that's done professionally and properly, that's really good because there's a lot that previous experience can actually tell us. But quite often you find that people will make very bland, simplifying assumptions. They'll say, oh, eVTOLs, we don't really know how they behave, so let's just treat them as big helicopters. Let's just use what we know from helicopters. So in a helicopter, if you think you can have a fairly simple outwash pattern, then perhaps you just use a fairly simple measurement technique. And that's exactly the problem. That's what the kind of way that the community is developing at the moment. So a lot of time is spent trying to educate people to understand the differences between helicopters, eVTOLs, how they might be different, how this world of the future, when we do have, let's say, ubiquitous eVTOLs everywhere, how we need to change our ideas, how the science can actually inform us. So in discriminating fact from fiction, the idea that I really want to leave in your minds is that physics gives us the truest guide. I can pontificate, I can make all sorts of assumptions, I can make all sorts of guesses as to how these vehicles will behave, but how do I actually know that I'm correct? And the fundamental way of determining correctness is to go back to the physics and do the simulations, to do the hard work, to do the measurements, to actually figure out what's really going on in the real world. Isaac Newton died a few hundred years ago, but he still rules what actually goes on in the physical world here. He doesn't get contradicted. If your recommendations or your prognostications don't match with what Isaac Newton says, it's very likely that you're the person who's wrong. So that's something to bear in mind. But as we advance our understanding of physics, perhaps we can make progress. We can go from very simple, bland and benign representations of our understanding to things that are slightly more complex. Once we have those slightly more complex understandings, we can build on those using these basic physical principles and march outwards and improve our understanding and hence the safety of aircraft operations in future. And that's essentially what my career has really, really been all about. It's trying to use the physics to understand the aerodynamics of helicopters and rotorcraft better so that we can actually make them safer and more reliable vehicles for a future public to be able to use them with confidence and security. So I'll stop talking there. A couple of conclusions. I would say the biggest conclusion is there's really so little time and there's so much still to do. So if you're thinking of a career in this particular field, there are a multitude of different places where you could join in and you could make a serious and solid contribution. I think you can see that I've been fortunate in my career path. Lucky even. There have been a few very lucky breaks and I've been in the right place at the right time. And I'm very grateful for that. And although perhaps the presentation looks as though it's all about the science, it's not really. It's about the people. It's about the people that take you along the way. It's the people who don't get the full credit, if you like, for actually having been there at the time and given the great ideas. So there's a spectrum of folk that I've known over the times. And I love this cartoon. It kind of brings things a full circle. Who got to the moon first? Well, certainly Hergé in his mind. Whether it was Neil Armstrong in practicality, there were people who were dreaming and were looking forward to this prospect. So sitting here in 2026, what can we dream about? What is the future actually going to look like? And we can only speculate, but I think it's going to be a really exciting future. Okay, so I'll stop there. I hope there are a lot of questions.
Thank you so much, Richard.
And I'll
What a
stop sharing.
wonderful talk and what an inspiring career. It's wonderful to hear you talk about your work and how passionate you are about it.
It's a pleasure.
Absolutely, Richard. Now, what a fascinating deep dive into the history of aerospace and the physics of flight. I think the amount of questions that I have, and we definitely don't have enough time, and I can see the amount of questions also popping in the chat. It's been brilliant and definitely, I think, spoke to a lot of us in it on so many levels. If I can take the liberty to ask the first question, if that's okay,
Idea.
let's probably start with something that one of our attendees have contributed. They are a graduate from a university who studied an aerospace engineering degree, and they are considering pursuing a career in helicopters. But really, helicopters or anything aerospace, what would you advise for anybody who's just starting out, recent graduate, early careers individual? How do you get into the sector?
Into helicopters specifically, or let's say
Let's
rotorcraft
start
as things.
helicopters and then maybe anything else for
Aha,
wider aerospace. Let's start
yeah.
with helicopters.
Oh goodness me, there are so many different avenues into the discipline these days. So the future helicopters, okay, there's going to be aerodynamics, there's going to be structures, there's going to be all the sort of conventional aerodynamics or engineering subjects that you might imagine. But the helicopters and rotorcraft of the future are going to require computer scientists. They're going to require AI specialists. They're going to require a huge range of expertise that we probably haven't even realized that we need just now. So that's one thing to bear in mind. The other thing is to make yourselves attractive. Now, how do you make yourself attractive to a prospective employee? And what are the prospective employees out there that you might consider approaching? Perhaps that's the easiest question to answer first. In terms of prospective employees, there's everything from the large primes, people like Leonardo, Bell, Boeing, Sikorsky. I've probably forgotten a few that I should probably mention, all the way down to guys who are producing remotely piloted vehicles, UAVs, the drones, the kind of things that are used militarily in Ukraine or for carrying Amazon parcels in parts of the United States. So the thing to realize is just how vast the prospect is. Get yourself into one of those slots, and you'll do well for yourself. What are these employers looking for? They're looking for people with enthusiasm. They're looking for people with knowledge, good education, experience in undergraduate projects, in postgraduate projects, in relevant fields, in relevant disciplines. Not necessarily with good marks, but people who actually know what they're doing, people who have the engineering sense to be able to make a contribution into these fields. And I've interviewed enough prospective employees for these companies, and you kind of know within a few minutes as to whether somebody is going to be a good fit with your organization or not.
No,
Thank
I love
you.
that. And I think that definitely relates not just to the helicopter industry, to all of aerospace and indeed very
Absolutely.
much any sector.
Mm,
And for those of you who were yesterday on our Open Skies Pathways program, I was talking a lot about kind of setting your goals, yes, but more than anything is following through, is coming up with a plan of action and showing
absolutely.
up and doing your work diligently.
Mhm.
And the opportunities will be there and doors will open, but don't start with the plan of being on the cover of a Forbes magazine. Start with an idea and the vision of becoming your best self at whatever you're doing, whatever field you're in, whatever yeah, but any part of your life, and
Mhm.
try and perfect that and show up and do your 100%.
Exactly.
um
I
yeah.
think if I was to embellish my answer, I'd say you can never know enough. You continue to learn. Never give up learning. Never give up reading. Never give up finding the latest articles and figuring out where the industry is going. Um, as a bit of inspiration to folk who might find school a little bit difficult, you can never know enough mathematics. Mathematics is the language of engineering. If you want to get involved in engineering, you need to be competent at mathematics. And that's it's yeah, you got to speak the language, you've got to know what you're talking about.
Absolutely. Lydia, I know you had several questions. I'm going to hand it over to you for any technical stuff, any non-technical thoughts, anything you
Well,
had
first
in.
I wanted to ask Richard, you mentioned you have been very lucky in your career. I think it's more the talent that has taken you where you are today. But I wanted to ask you if you can tell us a bit about the barriers you faced as well in your career and how
Yeah.
you overcame challenges.
Okay.
I'm
Yeah,
sure
so
you didn't have it easy all the time.
I don't know. I don't really like the word barriers. It kind of gives sort of like a sense of desperation. And I think the key to barriers or obstacles. I mean, life is full of obstacles. The challenge of life is how you deal with the obstacles that are put in front of you, right? And I think quite often the key is to who you take along with you. If you've got somebody good who can lift you up, those obstacles which seem so very, very high on often not as high as they seem. So surround yourself with good people, get good advice, and realize what's good advice and what's not. Realize when you need to follow your brain and when you need to follow your heart as well. I think that's something that's really, really important. Not everything is a logical decision. A lot of things are, but on occasion you've just got to take a chance. You've got to say, hey, given these two options, do I stay at Imperial College and become a professor in 10 years' time? Or do I go and form my own company? What do I do? In that case, that wasn't a decision I naturally had to make, but I had a similar one. Do I stay at Imperial College or do I become a professor at Glasgow University? And I agonized. I sat there for I don't know how many hours writing a little list of pros and cons, like a I don't know what do you call it, like a SWOT analysis almost. And then one of the old graybeards, probably my age now, walked into my office and he said, "What on earth are you doing?" And I said, "Well, I'm trying to decide. Do I go to Glasgow or do I stay at Imperial?" And he said, "What did your heart tell you?" I said, "Oh, okay." Pulled up my little piece of paper, threw it over my shoulder, and and on I went. So, like what I'm trying to say, I think, is, you've only got one life. It's not a stodgy thing. You take your chances. Sometimes you make calculated decisions on others, and life has a way of turning out. Those obstacles are not necessarily as big as they look at the first instance.
Oh, love it. Sorry, I know our audience who will be watching the recording can't see the amount of reactions I'm putting up and putting love hearts on repeat. No, Richard, thank you for sharing this and for being honest. And I think as people go through life, probably those of you who are just at the start of your career, you'll be thinking, I think I would definitely advise for you to say yes to most opportunities, because probably at the start when you are just building your CV, building your experience, getting good, saying yes to opportunities and trying things is one of the most important
Mhm.
things you can do. Being there, showing up to webinars like this and any opportunities. But as you get older, I think it's certainly important to exactly what Richard's saying, listen to your heart. and sometimes learn to say no to things as well if they
Hmm.
don't align with your values, with your vision for the future. But I think probably at the start of your career, I certainly did that. I was everywhere, and I definitely think whether you go somewhere you like, whether you understand then that you haven't actually you've started taking part in something you don't see pursuing in the future, all those experiences are useful. But then later on, yeah, listen to this.
Yeah.
I love this. This is brilliant. Richard, I can see some of the questions about
Hmm.
air mobility, and this is something that's near and dear to my heart. My
Hmm.
background is in electric
Of
aviation.
course.
Can I just also ask in the chat, how many of you guys have heard about eVTOLs before today? Just so I can take a step back as well and explain what we mean when we say eVTOLs or future flight. If you haven't, please put it in the chat. Um, I'll be happy to explain. But also, you said yes. There's a lot of people who say I have a dream. Hundreds of air mobility vehicles in the air. Yeah, certainly heard that quite a few times in my time in the sector. But what is your vision of the future? Not what's possible, but what's real
Hmm.
in your opinion? And linking it to the question from William as well, um, how do you see, do you really think that the air highways are going to happen if all of the eVTOLs and delivery drones are going to come to fruition, if this
Hmm.
is actually where we're going to get to? What's your vision of the future?
Okay. Yeah. Now, bear in mind, I'm a lowly aerodynamicist, right? Many people have tried to sort of pontificate on the future of this particular industry, and all you need to do is spend 10 minutes on LinkedIn to get into some very acrimonious discussions on just where things are going. So what's my thought? I think some of there's a spectrum, right? On the one side, you've got folk who say that this is never going to happen for various reasons. On the other side, you have people who have overly grandiose visions of just how the industry is going to pan out. And I think it doesn't take a genius to realize that the truth is probably going to be somewhere in the middle. So whether you're going to have 1,000 vehicles operating out of Heathrow or you're going to have 10 a day, that's bracketing the number. Whether the kinds of technologies that we're seeing being developed right now are the be all and end all, or whether they're a stepping stone towards something different, which will materialize out of the assembled knowledge that we're bringing together in exploring this huge new design space. I'm not so sure. I think it'll be interesting to see if the kind of incumbents that you see in the field at the moment, so the Jobies and the Archers and the Verticals, are still there in the form that we recognize them at the moment, given a few more years of advancement and development. If you have a look at something, this is a long-winded answer to a relatively simple question, but if you have a look at the classical helicopter, it's a crystal of engineering purity. The elegance of the fundamental engineering there is so absolute that you wonder how on earth people could have done that in any other way. And we can go into flapping equations and one per rev resonances if you really want, but that's the key to it. Helicopters are elegant. You have a look at your 20 rotor eVTOL aircraft developed by some obscure company in the middle of somewhere, and you hardly say that those vehicles are elegant. They're like an engineering, I don't know, mishmash brought together to solve a problem. And you kind of get this feeling from, especially from an aerodynamicist viewpoint, that this is not the be all and end all, but it's a stepping stone to something which will fulfill all the dreams that we have of electric, environmental, vertical takeoff and landing. So that's basically me. I suppose that would kind of like put me slightly on the sort of skeptical end of the spectrum, but I think I'm a sort of like a hopeful skeptic in the sense that I can see a path through to the future. And that's what I do on a day-to-day basis, right? I advise people. I sit in the background of engineering teams, basically saying, okay, look, have you considered this option? Do you think this is the best way of doing things, or are there better ways of doing this? Do you know about the stuff that we developed in the 1920s that's sitting in the textbooks you probably don't even know about? And how applicable is that to what you're doing now in the 2020s? So yeah,
No,
it's an evolution.
thank you, Richard. I had my air mobility fix. Love it. Thank you for the answer, and hopefully, William, that's you found it useful as well. Lydia, over to you for a few
Well,
thoughts.
we have one question from Nathan as well, who we haven't addressed yet, so maybe I can read that for you, Richard.
Hmm.
So Nathan is asking, why does rotorcraft certification take so long and why is it considered an obstacle? I also want to highlight the AW609 tilt rotor, which has been in development for more than 20 years and still hasn't been certified. And what challenges will eVTOLs face with certification?
Mhm.
Very interesting point.
Okay,
Question.
you'll need me back for another 3-hour lecture, I think, to cover that question in full with yeah, in full detail. But yeah, look, it's an important question. So first of all, I'd take issue with the word of certification being an obstacle. It's not an obstacle. It's a fundamental protection that you and I rely on so that these aircraft are safe when they come into contact with us and the remainder of the public and the things that we hold dear. So certification is not an obstacle. It's an inherent part of making a safe transport ecosystem. Why does it take so long? Well, it's a difficult process. It's not a trivial process. Now, if you come to advanced rotorcraft, things like the AW609 and eVTOLs with their multiple rotors, you can imagine sitting in the regulator's office and trying to decide, okay, on what basis do we actually put in the rules which will govern how these strange new animals actually work in practice? So what do? Are they helicopters? Well, yes, but are they something else? Yes, but not quite. They have elements of helicopters. So how do you actually decide on what basis? How do you construct the rules that will actually apply to this new generation of aircraft? And it's not a process that can be invented overnight. There's a lot of learning involved in doing that because these aircraft are new in terms of their concept and the way that they function. So part of the process is actually the designers of these aircraft, the originators of all this technology, working hand in hand with the folk who make the rules to actually figure out how we actually make rules that everybody can agree to, that everybody can actually conform with, that will actually then be effective. And this is the really important part, right? That will be effective in certifying that these aircraft are safe to be wheeled out of the hangar, a person put into them, flown for various test flights, and then passengers, for example, loaded into them. And then for those passengers in their aircraft to be flown over us, who standing looking up and wondering at this brave new technology that's flying over our heads. So it's a long and complicated process. It's inherently complicated. And that's why, for example, the process for the AW609 has taken so long.
Thank you so much,
Hopefully that
Richard.
answers your question, Nathan, in
Let
some
us
detail.
know, Nathan, and let us know if you have any other question, follow up. Do you want to ask a question, Maria, or should I?
No, because otherwise I'm going to dominate because I think we definitely are going to have you back, Richard.
All right.
So I'm going to keep my questions for next time. Lydia, let's have you for the next one. I know you also had some thoughts.
So one question I had is that do you think that so you talked about vortex brain state and
Mhm.
outwash. Do you think these are the main limitations of eVTOLs flying in cities and us
Oh,
using them, or are there other limitations? Or is this, in terms of aerodynamics, are these the main limitations?
okay. I wonder who's sitting on this call that might get this little message sent through to them. But those are the two at the top of my list, right? I've got this whole list of things which we really need to have, talking seriously now. There are a whole list of issues which we do need to address. Vortex ring state and outwash are perhaps two of the most pernicious ones, given that there's a lot of pressure to get these aircraft off the drawing boards through their test program and into civilian use.
Yeah,
So,
so these are the
so
most dangerous ones, you would
they're, the-
say.
they're the first ones to tick off the list. If you
Yeah.
if you've got an aircraft that's subject to vortex ring state, you don't want that anywhere near a constrained landing pad stuck in the bottom of an urban canyon. If these aircraft do produce excessive blasts of wind out as part of the outwash, you don't want to bring those aircraft into close proximity of vulnerable people or anybody for that matter. Or you don't want to even put up a glass window within a certain distance of these vehicles, right? And that's the kind of thing that's kind of it's where some of the sort of leading proponents of eVTOL are already going towards building vertiport infrastructure, towards designing operational routes which will allow these vehicles to operate out of that infrastructure. So they're the kind of like the immediate issues to be addressed. But there's a raft of other things which will keep us busy for many years. Now, I don't say that as like a threat to the industry or a kind of like a doomsayer. I see that as a very positive thing, especially for folk who want to go into engineering, because
Yeah, there's a lot of opportunity
absolutely,
to do more, to investigate, to
mhm,
create, design. It's very exciting.
absolutely. There's a wide range. If I still had PhD students, and I don't think I'd want 20 of them, but a good bunch would be would be gainfully employed.
Do we have any other questions in the chat? Yeah, Nathan replied, awesome, thank you. Yes, absolutely. Safety is vital, and the aerospace industry can be conservative by nature.
It has to be conservative. If it wasn't, I think we would have a bit of a problem on our hands.
No, no, this is all brilliant. Thank you so much for the discussion and for the questions in the chat. I know a few of the students said that, or a few of the young people said they wanted to be pilots as well. I think this is the questions that the industry is yet to address will be there for are challenges for everybody.
Hmm.
Yes, there's plenty of engineers who are trying to put their hats together, their heads together to resolve these in terms of aerodynamics, in terms of safety, but there's also loads of regulators, there's loads of pilots that will need to figure out how to pilot the aircraft safely, how to ensure the safety of people both in the air and on the ground. Air traffic management was mentioned as well. Can we really make sure that the skies of today that are going to get busier tomorrow, are they safe? Are they connected enough in terms of have we got the visibility of all the aircraft that are flying at all stages, at all different altitudes,
Hmm.
etc. And when we are going to have different levels of aircraft flying with drones and helicopter drones, air taxis, eVTOLs, helicopters, commercial aircraft, etc. flying, how do we make sure that all these aircraft communicate together? I think there's so many different challenges, but to me it sounds exciting. To me it sounds like, as was mentioned, that there's so many career opportunities available, regardless of whether engineering is something you want to go into, aerodynamics is something you're considering, or maybe it's something that doesn't even exist. When I started my degree, aerospace engineering, air mobility and electric aviation was nowhere near as popular as it is now. And I was the first person in my university to do a dissertation looking at
Hmm.
electric aviation. And loads of people were thinking that I was completely insane, talking about sustainability and drones. And here we are today with so many projects being funded by the UK government here in the UK, but also developing all around the world. And I'm so excited to see that loads of our audience members are also considering a career in this field and seem to know stuff and genuinely ask fantastic questions. So I'm really excited. I'm like, yes, we need more people
Hmm.
entering this sector.
Absolutely.
Um, Richard, this has been absolutely brilliant. We've had a question whether it's okay to connect with you on LinkedIn and maybe stay in touch. Would you be open to that as
Absolutely.
well?
Yeah. Yeah, absolutely. Go ahead. You'll find me pretty easily, even though I've got a very common name. Um, so yeah, just drop me a connection request. And if you've got any questions, fire away. I know this is very short and sharp, and sometimes folk take a bit of a time to think up stuff. So go ahead. My question
Nice.
would be to you to I started my slide by showing Artemis, and I kind of made the analogy with Apollo. And I wonder to the modern generation of engineers what Artemis actually means. Does it mean the same thing as Apollo, or is it something completely different? And perhaps is eVTOL the new Apollo rather than Artemis? I wonder. Let's try and keep our feet on the ground, but reach for the stars, I guess.
No, I love this.
Beautiful words.
Thank you so much, Richard. Can we do another round of virtual applause to Richard? And thank you so much
Thank you
to
so much,
Lydia
Richard.
for co-moderating and for inviting such a wonderful speaker, and to everybody in our audience for all your engagement and all your great questions. Just wanted to very quickly share as well that this is our final webinar that we are going to do as part of a welcome, or I suppose available to all, and from now on, our future Engineers Career Spotlight and Pilot Career Spotlight webinars will be a part of our membership offering. And if you want to stay in touch with Flight Crowd and be a part of that community, I know Richard spoke a lot about people. We very much care about the people who will be shaping the skies of today and tomorrow. you want to be a part of this, join our Flight Crowd WhatsApp community, become our member, join our programs, our events that we have, become a volunteer, stay in touch because we need you all, but also the aviation industry needs everybody, and we can do so much more if we join our forces. So I invite you all to stay in touch and stay connected and reach out if you have any questions, any thoughts, and we're looking forward to continuing to support your career journey. But in the meantime, thank you all, and we look
Thank
forward
you.
to speaking to you soon.
Thank you so
Thank
much. And
you.
thank you so much, Richard, for coming today. It
Thank you
was
for
very
having me.
inspiring.
Thank you for having me. It was a pleasure.
Thank you all. Take care
Thank
and
you.
have a wonderful evening.